Okay, so we left off on Monday talking about a big question, where do we come from? Why are we here? Now we're getting back to reality in terms of looking at amino acid sequences. So now, if you've made your bracelet, that assignment has been created in Canvas. So just upload a picture, write the sequence, slam dunk, 12 points. So as I said, there'll be 5 activities in place of the Module 5 exam. I have 4 of them pretty much set in terms of what I want to do. The 5th one, I want to see if we can use that program AlphaFold. I've gotten some feedback from Dr. Huang on that. I'm not sure if that will be possible, but we'll figure something out. He stated that 10 amino acids is probably not a long enough chain to give any reasonable prediction of anything, so I'll think of something. Any questions before we get started? So what we're going to start our journey on now is that we know these building blocks, the amino acids, and we're going to start talking about sequencing them. And what you have to imagine is happening, although we're only talking about it on a very small scale, is that you have really long sequences. So when you have a long sequence, eventually that will form a peptide. But for the organic chemistry part, we're talking about very short sequences here. So a peptide can be considered a biopolymer. And so polymers have monomers of repeating units. So the repeating units here are amino acids. So the monomers, it's not like one chain of one amino acid. So they're going to vary from position to position. But overall, we're talking about just bonding amino acids together. And so they bond through an amide bond. So I'll highlight that here in red, maybe if I can choose the right color. So it's highlighted in red. Those are amide bonds. So we've talked about those in Module 3, I believe. And under this module, and then moving forward in biochemistry, this is it's called a peptide bond, but essentially it's an amide bond. So they mean the same thing, just different words. And as shown here, we have 2 amino acids, alanine bonded to valine. And so we see from the 3-letter abbreviation, see this little hyphen here in the middle? That's to designate the peptide bond. And what will happen, again, as you move forward in these classes, rather than using the 3-letter, everything's abbreviated to the 1 letter. So Alaval is abbreviated AV. An isomer of that, so contains the same amino acids but in a different sequence, is now VA. And so those are 2 different things. And so I want to show you how we're going to read this, what is the sort of common thing, common things we need to know. So we're always reading left to right, and in doing so, there's an N terminus. So on the left is the N terminus, and on the right is the C terminus. And so now knowing that, we can say, yes, AV and VA are different. And so what I want you to imagine is, okay, now you have, an N number of amino acids in there. One's going to be the N, and the other end is going to be the C terminus, followed by everything in between. So peptides are structures that make up proteins. So you get this long amino acid chain. Eventually, it's going to start doing things conformationally, folding back on itself, forming hydrogen bonds. And eventually that forms a protein. And those are enzymes that carry out reactions under physiological conditions. So all the reagents that we've learned in this class, that's stuff you do in the lab in a glass vessel. Enzymes are the reagents that do things in your body. So your body is the reaction vessel under physiological conditions. So the 4 elements for protein structure: primary, secondary, tertiary, and quaternary. So primary, which we'll focus on for the most part in this class. The other 3 are what you learn later on. Primary is the exact sequence of the alpha amino acids. And again, we're recording those as left to right as we read the sequence. The secondary structure arises due to hydrogen bonding between the amino acids. So as you grow these things out in a line, we know that sigma bonds can rotate. So there'll be rotations happening, and things will sort of backbite on one another, so they're closer together, and they'll associate through hydrogen bonding. The tertiary structure is the complete 3-dimensional conformation. And then quaternary is the association of 2 or more peptide chains. So as I said, the left side is the N, the right side is the C. So now imagine the scenario of you're given, like you made your 10 sequence amino acid bracelet. And if you've gone on to the Canvas assignment, you now see the key of what those amino acids are. But imagine you didn't have that key. How would you figure out what the sequence of those amino acids are? So that's what we're going to spend time doing today, and looking at the logic of how that's done. So in determining the primary structure, that's the sequence, a classic reaction is amide hydrolysis. And so this is typically done with concentrated HCl, so 6 normal HCl at forcing conditions, so essentially boiling water. And what that is doing is hydrolyzing all the amide bonds. So again, I can't stress this enough, I'm just showing 2, but imagine if there's 100. You cleave all them, and then you can figure out a way, okay, I have 5 alanines in here, 10 tryptophans, et cetera, et cetera. So as I've shown here, I'm going to say HRMS. So that stands for high resolution mass spectrometry. And notice the exact mass of AV is 188.11609. And the more decimal places you're able to measure with these instruments, the more specific you can then get back to the molecular formula. If the number was just 188, then you could have a lot of variability in that. But as you go out in the decimal places, it's really limiting the possible molecular formulas. And then when you hydrolyze that, you get the 2 amino acids with their exact masses. And then you can say, okay, I have alanine and valine in there. But now the issue is, this technique does not tell you what sequence they were in. It's just telling you that these 2 are there. So as a review, how many unique carbon signals would we see in this dipeptide? So we'll just put dots over each of them as we walk down the chain. So 1, 2, 3, 4, 5, 6. The methyl groups are the same, so it's 7. And based on carbon NMR, you could kind of get an idea of, what amino acids are in there. And again, this is a point at which all of these instrumental techniques come into play to really figure out what the structure is. So 7 unique signals, and now it says how many would be in that region, 180 to 220. And so these are going to be your CsP2 hybridized carbons. And so of that, we have the carbonyls. So 1, 2. So 2 of those 7 would be in that region. The other 5 are going to be more like 0 to, say, 70. So now to put that into context, so imagine you have an unknown peptide. It has 3 unique amino acids present by NMR and mass spec. How many possible sequences are there? Any mathematicians in the crowd? I'm sure there's some equation you can just shove those things into and it'll spit it out. But I've neglected to put that on this slide for the last 4 years. So maybe we'll just start drawing some stuff here. So let's say A, V, and F. So we'll use those as the 3 unique. And now what we're doing is just making sequences. And again, I have my laptop open to verify, not cheat. So let's just move things down here. So F, A, V, V, F, A, so we can do V, A, F. So we have VFA already. So A, VF, F, VA. AF, V. So that'll give us 6. So I'll write look up formula. So you won't benefit from that, but the next class will.
It's 3 factorial.
Is it 3 factorial? Okay. So we'll write that. So we'll say, just to generalize it, n factorial. Is that?
I wouldn't really know. I'm not good enough at math in the equation. Let's know that specifically.
3. So that's 3 times 2 times 1. So now you can see the issue. You know, if you're in lab and you have the substance, you can get these 6 possible sequences, and you want to be able to assign the exact sequence. So over the next couple slides, we're going to learn the reactions on how to do that. and then we're going to expand it out and look at the problem a different way. When you're given fragments, how can you take the fragments and put them back into a sequence? Any questions? So we'll learn a couple chemical reactions on how to do this, and then we'll learn some enzymatic methods that react very specifically with certain amino acids. So the reactions we're going to learn primarily act on the N-terminal residue. So I'm going to use that term as well, residue. So remember that that's on the left. And so the first one is called the Edman degradation. And so the reagent that is used is shown below the arrow here, phenyl isothiocyanate. And so this central carbon here is sp hybridized. And that's going to make it electrophilic. So what happens is the N-terminal nitrogen, so I'll circle that one, it's going to attack that reagent, cyclize, and then eject off the rest of the chain. So even though I'm only showing 2 amino acids, imagine if the rest of the chain was longer. All it's doing is chewing off the N-terminal one at a time. When it does that, it's forming this thing which is called a phenyl thiohydantoin. And so I'll highlight in red here. So that's the atoms that come from the reagent. So that mass is constant, right? 135.01427. Now what will change is the mass of the hydantoin you're forming based on whatever amino acid is at the N-terminal residue. So I'll highlight that in blue. So basically, you can make a library of these thiohydantoins, get their masses, and then as you start determining your sequence, you say, okay, it has this mass, so the N-terminal of that sequence is alanine. And then in this reaction, you're left with valine, but imagine you have 50 more down the chain. And so you could essentially do this one by one. Just take that N-1 chain, repeat it. Now you have the new N-terminal residue, boom, boom, boom. But of course, that would take a long time, right, in terms of the sequencing. So if you have this tetrapeptide cis-cer-val-phe, and you subjected it to 2 consecutive cycles of the Edman, what peptide would remain? So we'll say cycle 1. Cycle 2. So with each one, off the first one, you would determine it was cis at that N-terminal and then cer at that N-terminal. And so this would leave us with B. So there's many ways to do this. And another way, I'm gonna use this word tag. To tag the N-terminal residue is using the Sanger reagent. So that's 1-fluoro-2,4-nitrobenzene. So interestingly enough, if you look at the bottom of the slide here, Sanger actually won 2 Nobel Prizes for his work on determining the structure of proteins. So what happens is that you can see from this reaction that N-terminal residue nitrogen gets tagged. And the mechanism for this, we didn't talk a lot about. It's called nucleophilic aromatic substitution. So you see the fluorine has been substituted for the N-terminal nitrogen. And now with that amino acid tagged, essentially it's going to be subjected to a hydrolysis. So you're going to clip that off. Now you have this amino acid with a known molecular weight tag, and then you just compare it to the existing libraries. So the digestion step in this case is using sodium hydroxide in water at 100 degrees. We're now clipping off that N-terminal residue, and we're ending up with the tagged alanine here that has a mass of 255.04914. So the logic holds, you're just using a different chemical tag. So again, these are sort of classical reactions in the evolution of how this was done. But again, the high-res mass spec is crucial in facilitating this sequencing. So over the next, I guess the rest of this lecture today, we're going to use some of these problems. We'll use these sort of colored balls with the amino acids based on their classification. So polar, nonpolar, acidic, and basic. And so the color is just there for a visual thing to help spice up the sequence a little bit. But again, those are the four classes we talked about. So our first question here is, we have this peptide and it's been digested and found that there's 12 amino acids. So the composition, what's shown here, that's not the sequence, that's telling you just how many of those are present. And so we have to use the fragments shown and then piece it back together to find what the sequence is. And it says, the N terminus is Sir, the C terminus is Cis. We might figure all this out on one slide, and the subsequent slides are just the individual questions. So looking at, we have Sir and Cis, but then looking at the composition, see how there's two of each. So what we need to do is look at these fragments and see where there's overlap in the fragments and sort of line them up, cross out sort of the common ones, and then get the whole fragment or the whole sequence. So So how many questions do we, okay, so we have 4 questions on this. So what are the first 3 amino acids of the sequence? So if you look at those fragments, it said, again, we're reading left to right. It says cis has to be at the C terminus. And we see these 2 here, right? Cis and cis. You see this one's internal, or it's going to be internal. So that cannot be at the end. So one of these has to be at the end. We need SIR at the left side. See this one right here, that's in the middle. So that SIR cannot be over here, which means that this one has to be the start. So serine, leucine, tyrosine. And now I think the most straightforward thing to do is sort of look at something that connects that to another fragment. So we've taken care of that. So the next thing is leu, tyr. And so we have 2 of the leucines, right? And the overlapping one is here. So see how those 2 overlap? So that means the next amino acid has to be glue. So we're taking care of that. So where do we see the glues now? So we have that, glue, leu, glue. So we can we make another overlap? Maybe let's try, we'll go to the right side because we know that the cis has to be there. So we have to use that over here, right? So let's stick that in there and then see if we can get some more overlaps. Okay, so we have SIR, val, cis. And now this fragment in the second row, see how it has SIR, val right here? So that means we're going to use up that other cysteine now right here. And so now if we look at what's remaining of the cysteines, there's the tyr cis, this one. So that means that cis and that one are the same thing. So now we're there, so we got that. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need to do some more overlaps here. So glue and then tier are what we're working with to sort of stitch them together. So since this fragment ends in tyrosine, and that's sort of where we're at on the right chain, we can say glue asp and that would take care of that. And now we have these two fragments, glue and then glue, and we see the last one. So those have to be connected by the leucine. So I think that's the correct sequence now. So if you have like an empty sheet of paper, you know, like on your college ruled notebook, like on each line, you can sort of like do this overlapping a little bit clearer so that by the time you get to the end, when you put those fragments in, you can see how they've all overlapped to make the sequence. So that's pretty much the logic. The questions can get a little bit more challenging based on the way the data is presented to you. And so there's one in particular that we'll go over it takes some head scratching to figure out based on the reactions and the rates of how you get the fragments. So the next couple questions, so this was just says what are the second three, what are the third three, and what are the last three. But again, you're going to use the logic of what's the N terminus, the C terminus, how do things overlap? Are you getting that proper overlap? Any questions at this point? Okay, so this is that problem. But now this will sort of introduce activity 2. So exam 5, activity number 2. So this is practice for doing that activity. We're going to do it with that sequence we just found. But for your activity, you do it with your bracelet that you made. So, glue, tier, glue, asp, tier, cis, val, cis. So that was the sequence. And so the activity now is, I want you to go onto this website called bachem.com. And as a tab in there, they have this thing called Knowledge Center and Peptide Calculator. So if you go in there and enter that sequence, it's going to spit out a bunch of stuff for you. And essentially, you're going to do that as an activity for your own thing, but we'll walk through it now. So I'll give you a minute or two to shove that sequence in there, and then you can tell me what the molecular weight of the peptide is. So for N-terminus, I think you have to pick like NH2 and C-terminus CO2H. Anybody got fast fingers figured out yet? What sucks is when you're on the phone and you're trying to move the cursor and it won't go to where you want it to go.
Or autocorrect.
Yes. What'd you get?
I got 1,422. I don't know if it doesn't know.
It's close enough.
Close enough.
So again, in the menu there, when it says choose N-terminus and C-terminus, choose NH2 and CO2H. So I think it should be 1423.58 or thereabouts. And so once you do that, it's going to spit out a bunch of other data. And then the next couple slides are on questions on that. Anyone else confirm? Does nodding mean yes, or okay? We have some nods. So what is the isoelectric point? Huh?
At 2.93.
2.93. So remember, on Monday we did that for the individual amino acids. And so now sort of the difference is when you have a sequence, your internal nitrogens are now bound into amide bonds. And so you have your N-terminus, your C-terminus, and really what else is going to affect it is any other acidic or basic functional groups at that point. So what's the net charge at pH 7? So negative 3.09. So as long as you understand how this stuff is arriving at those numbers, then you can just use the software to automate it and do it faster for you. But again, that's all of the logic we covered on Monday. And then the average hydrophobicity.
-0.17.
So negative 0.17. So God bless all of you going into biochem, and you have to understand the difference between hydrophobic, hydrophilic, lipophobic, lipophilic. So those things will matter in terms of, once you get these sequences and they form these proteins or enzymes, you have like the outside area, right? And then you have the internal cavities. And so they'll throw these terms out: hydrophobic, hydrophilic, lipo means fat, so lipophilic, lipophobic, depending on what they're talking about in terms of like the cell media, that sort of thing. So hydrophobicity, so that would be water hating, I think. And again, if the majority of the cell is sort of aqueous or whatever, this is telling you the more polar amino acids are going to interact with water, and the non-polar ones are going to be shielded from that. And the final number, what is the ratio of hydrophilic residues to the total number of residues?
42%.
So 42%. And even though it's spitting that number back out to you, it's important for you as a student to understand, okay, what does that mean? Structurally, how is that significant? So essentially, that's going to be your second activity. You'll go to that website, shove in your sequence from your bracelet, take a screen grab of the results, upload that into Canvas, and that's activity number 2. Any questions? Okay, so for the last 30 minutes here, we've talked about sequencing the primary structure using chemical reagents. Now we're going to get into, I guess, one more chemical one, but the enzymatic methods. And so these next couple ones are not reacting at the N-terminus specifically. They can, but it's not specific just to the N-terminus. So again, HCl is sort of indiscriminate. It's going to digest every peptide bond. Another reagent that's used is called cyanogen bromide. So this is Br bonded to cyanide. And it cleaves a peptide chain in a very specific way, and it only acts upon methionine or met residues. So again, when you're reading these things left to right, and you hit a specific amino acid, so this one's methionine, this one it's cleaving to the right of that. So you have to read it first and then it cleaves. So it's not cleaving before it. So we have how many here? 1, 2, 3, 4, 5, 6, 7, 8. So you'll hear these different words, like a dipeptide is 2 amino acids, tri is 3. You get to a certain point like this, there's 8. People would say this is an oligopeptide. Oligo's a lot of different things. When you get like really large, you just start calling them peptides. So as we're reading this, from left to right, proline, glutamic acid, leucine, lysine, valine, methionine. So at 6, boom, we hit it, and then it's cleaved right there. So now the methionine is the C residue. And you have 2 fragments. So again, think of, you're in the lab, you have this 8 amino acid oligomer, you don't know what the sequence is, you're going to run this battery of tests on it to figure it out. You hit it with the cyanogen bromide, it shows 2 new things, so you know, okay, since there's 2 things, there had to be a methionine in there, and it is now the C terminus of one of those fragments. So the 3 enzymatic methods are shown here. And so again, an enzyme is just a large biomolecule that's going to catalyze a reaction under physiological pH. And these are further classified as endopeptidases. So in terms of the nomenclature, things that end in ASE are typically enzymes. And the word of the enzyme usually gives you an indication of what it does. The 3 in this class are trypsin, chymotrypsin, and carboxypeptidase. So trypsin cleaves a peptide chain at the carboxyl group of basic amino acids, so lysine and arginine. So meaning that lys or arg end up at the C terminus of the new fragment. Chymotrypsin cleaves the peptide chain at the carboxyl end of aromatic amino acids, so phenylalanine, tyrosine, and tryptophan. So those are the ones with the aromatic rings. And the same thing, those will end up on the C terminus of the new fragment. Carboxypeptidase operates opposite of those chemical tags. So this one's going to start at the C terminus and then work its way right to left. So it's going to say, okay, I see a carboxyl group. I know that's the C terminus. I'm going to chew that off. And then you have another fragment with a new carboxyl residue, so it's going to chew that off. It does it sequentially down the sequence. So here's a visualization of trypsin, where again we're looking for lys and arg. So in these 2 examples, the first one, we're reading, so 1, 2, 3, 4, 5, 6, 7, 8. So the lysine is the one in dark blue. So once it hits 4, it's going to cleave between 4 and 5. And so now you have 2 fragments, each with 4 amino acids. In a different example, using arginine, this will cleave between 6 and 7. So now you have 2 fragments, one with 6 and one with 2. I think this is, yeah, this is, if you go on this website, so PDB stands for Protein Data Bank. That's the link to what trypsin looks like. So chymotrypsin, we're looking for phenylalanine, tyrosine, and tryptophan. So in the top one, once we get past amino acid 2, it's going to cleave there. So we have a 2 and a 6 in terms of the fragment sizes. The second one, it's going to clip here between tyrosine and methionine. And the third one, it's going to clip after the tryptophan. So those both produce 5 in 3 amino acid fragments. So in the carboxypeptidase example, the top sequence is the one that's used, so they're not different examples. We're starting with 1, 2, 3, 4, 5, 6, 7, 8. We're cleaving off the C terminal. So we have a 7. And then that 7 amino acid fragment is now going to undergo the same reaction with carboxypeptidase to cleave off the proline. And then for the 6, we cleave off the arginine. And so if you're able to measure the rate at which this happens, you would see that, so the carboxypeptidase is not just going to stop on that first fragment. You would see that glycine is going to be formed in the largest amount when you first start the reaction. Then you're going to start see proline grow in, and then arginine grow in. So as these things start to form, as time progresses, it's giving you an idea of where they are in that first chain. Any questions? Okay, so let's look at an example. There we have a sequence, and we're going to treat that with trypsin, which is going to read for lyse and arg. So as the enzyme is reading that, how many fragments will be produced? So there's going to be 4. So we're starting here. We're reading. We hit arg, so we're going to cleave there. So that's going to be 1. We hit lysine, cleave there. That's 2. We're reading. And we're going to cleave there. So that's 3. And then the glycine itself is 4. So those are 4 fragments. In terms of the number of amino acids, this has 4, 4, 2, 3, 6, and 1. So even though you see what those amino acids are, just imagine if this was an unknown substance. You run the trypsin reaction, you can say, okay, now by gel electrophoresis, I have 4 fragments. I still need to figure out what are the sequences of those fragments. So we sort of chopped it up on the prior slide, but the answer is B. That indicates what they are. Sequence. And so now I think this is the same. Now we're going to treat with chymotrypsin, and we're going to read for phenylalanine, tyrosine, and tryptophan. So we'll start here. As we read, we see the tyrosine, so we're going to clip there. So, phi, tyr, trip. I think we're going to read until here, and then clip. So that's 1, 2, read until here, and then clip, 3. We see phenylalanine's right next door, so we clip there. So 5. So this is 1, 2, 6, 3, 1, and 4 in terms of the number of amino acids. But again, compare it back to the trypsin, which was cleaving the same sequence. That gave you different fragments. And those are the fragments that eventually, if they were thrown on one page, you could backtrack to what this primary structure is. So this answer ended up being C, as we saw on the prior slide of clipping. Okay, so now it gets a little bit more challenging. And you're given fragments according to the reaction with either trypsin or chymotrypsin. So you have to remember what they're doing and then find the overlaps, put them together, and find the original sequence. So the first question says, what is the N-terminal residue based on this data? Say ILE. So yeah, isoleucine. So let me point some things out how we arrived at that. I'm gonna use the highlighter to hopefully help narrow things down. Maybe one thing first is that it's definitely got to be one of them that's on the left side of the sequence of the fragments, right? Because that's where the N-terminal residue is going to be. So in terms of the logic, the way we can eliminate some things, so met, his, phi. So that occurs here. And you can see that the met is blocked by the trip. So that cannot be the N-terminus. And then what other overlaps can we see? So this, I'll highlight in blue. So ala, seer, ala, gly, phi. So that lice, maybe I need to erase this part. And then what else can we overlap? So maybe in green. So met, cis, arg. I'm running out of colors here. We have val, cis right here. Then I'll have to go back to the, you can see that the lice, those should overlap. And so that's going to leave us this isoleucine tryptophan. And so through deduction, induction, whatever, it has to be isoleucine. So I-L-E, trip, and so I guess the majority of these are just asking different questions, but arriving at the sequence. So maybe on this slide we can just put the whole sequence so it's all in one spot. So ILE trip, cross those off, and then write from that longest sequence and now we've overlapped those green ones, so we go to the blue. So we're done with the blue. We see that phenylalanine is bonded to the lysine. And I apologize for going on the second row here, but lysine is then bonded to valine and then cysteine. And I think that accounts for all of the fragments, all of the amino acids. So ILE would be the N terminus, and then cysteine would be the C terminus. So this is the first time I've used color and highlighting, and I would say it's definitely easier for me to do that. I've taught it other ways that are probably not as helpful, but again, if you have a sheet of paper, you can sort of write these things where the overlaps are, and it'll eventually get you to the right answer. But I think the color helps as well, finding the patterns. And then you just overlap them, and yeah.
I know for me, so when I looked at it, I saw that trypsin has to end in the last word arc. And so cis would have to be the C terminus, and then for chymotrypsin, you would have to, the C terminus would have to be TRP. And so then I knew that cis, I just started from the C term pretty easy.
Okay. Yeah, so I mean, there's a lot of strategies that you can take. And again, if you're able to dial into that and apply the logic, but my caution would be that just check your work and make sure that everything holds for what you're proposing. But I mean, that seems like a reasonable alternative way to solve it. So let's see where, just go back and count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 amino acids. And so this question was the C-terminus. Let's go. This question, okay, how many amino acids? That is going to bring us to the end. So end a little bit early, but so there's a quiz using sort of this logic. Next time, we're going to look at some other things that can happen. Specifically with cysteine residues, they can form disulfide bridges. How do you deal with that when determining sequence? And then we're going to dial back. How can you make amino acids in the lab? That's pretty straightforward from what we've seen already. And then we just have Monday next week, is that right? Okay, so then once you know how to make them, how do you actually make amide bonds in the lab? So we'll review chemical methods of making the peptide bond. It's a condensation between an amine and an acid. To make that, you lose water. And I think that will be Monday's lecture. So I'll open up the activity 2 so you can get that sort of jammed out and complete. And then moving forward, activities 3 and 4 will involve taking your amino acid sequence and then figuring out the codons, if you've heard that term, that make those amino acids. So we have just like, what, 3 lectures left or something? So the end is near. It'll be here before you know it. All right, so yeah, we'll see you next week.